to be put together. That's kind of an abstract term, but think about like, um, if we have pictures of faces, clustering algorithm should be able to figure out whereas a face belongs to the same subject or the same individual, or if we had pictures of cats and dogs, maybe we don't need to tell the algorithm to cluster them together because the underlying inherent features will be able to provide enough signal for the algorithm to split them apart into separate clusters. There's no clear cut between these two branches of machine learning. There is some semi-supervised learning algorithms in which we draw some signal, but it's still being supervised automatically, especially in natural language processing. We see these for pre-training of large language models. But there's another big branch, which is the reinforcement learning. So the main difference is that in reinforcement learning, we learn by example. So we do not provide inputs and outputs. Instead, we let an algorithm to observe and state, which could be an input, and then interact with the environment. So this kind of abstract. So what could it mean? It means that we can let the algorithm do something with it. It could be a robot, it could be a simulator, or it could be something like a large language model eliciting a response and getting some feedback from users or from people. So in a sense, we're going to see more or less how this goes around. This repeated execution of the interaction with environments and the collection of a reward that is signal allows the algorithm to fine-tune its behavior such that this reward signal gets maximized over time. So as I was saying, reinforcement learning doesn't have a training data set. Instead of it relies on a simulator. We're going to see some examples of the lunar lander or the pole cart, in which the algorithm is going to execute those physics simulators and figure out whether it crashed the ship or not. And that's going to be enough for the algorithm to learn. And these algorithms basically learn how to make decisions based on feedback. So that's exactly why they're better suited for self-driving purposes or to create robots that walk. If you've seen those Boston Dynamics robots, I'm pretty sure that they have been trained with some flavor of multiple reinforcement learning techniques. So what makes this reinforcement learning different from other machine learning paradigms? If we had to summarize what I just said, we only have a reward signal, so that is the outcome. So was this good? Like if I'm navigating towards the destination, I need to take a turn. If I take a right, is it better than taking left? If I'm closer, then the reward might be better because we have reduced distance. So anything, yes, there's loss function, but we'll see how it fits in a moment. So hold that thought. So another key aspect is that this feedback is late. It's not instantaneous. So this is also very important to wrap around your mind around the concept of reinforcement learning. With supervised learning, you render a decision. So you pick a class, or you choose a set of labels, or you predict a quantity using regression. That's the end of it. With reinforcement learning, no, we are in a decision process. So again, going back to the self-driving example, when we are moving our vehicle, if we're getting closer, then we're on the right track. But we could derail the whole process if we take a detour and then start straying away from our goal. So that reward signal is what is going to tell us whether we're on the right direction or not. And at the end, if we get to our destination, then the learning process finishes. So these are temporal processes. That means that we're going to take, as I was mentioning, like multiple steps. Like maybe you're using blockworks, which is a simulator, to assemble a structure. So you need to choose a block, then you need to put in a position, then choose the next block and put it in a position, such that you assemble the correct structure that is the goal of the process. Therefore, the agent actions affect the next observation. So these observations are not independent of each other. That means that any decision that I might take is going to reflect the choices that I have in the future. So if I do a U-turn, then I may need to do a U-turn again to correct my course. But if I go into a one-way street, if I'm a self-driving car and try to get into a one-way street, then I'm going to get a penalty. I need to correct course immediately. Maybe my action is only to move out to the next available street where it's legal to drive, to avoid facing penalty or being stopped by a police car or whatnot. So all of this is modeled mathematically using something called Markov decision process. And basically that's it. So if you're developing a reinforcement learning algorithm, you need to define this mathematical structure in which you have a reward signal that we're going to represent it with this variable. Let me make the font larger. So it's going to be scalar feedback signal. So why is it scalar? Exactly because of the reason of Nitin's question. We need to implement the learning process using a loss function. But the loss function is going to be special. So we're going to see that in a moment. This reward indicates how well the agent is at a current discrete time step. So yeah, if I'm a walking robot, that each time step is going to be one step, like one physical step. If you're training a poker playing bot, each step is going to be a turn. So you may need to draw a card from the deck. You may take a decision where you want to fold, or you want to show, or you want to, I don't know, like raise the stakes of the game. And in the end, the driving mechanism is the maximization of the cumulative rewards. So what is a cumulative reward? It is that at each time step, we're going to observe these immediate rewards that gives us the signal, and we want to take the best decisions as frequently as possible. So the cumulative reward is just the accumulation of those individual reward returns into a single quantity. So in the end, the main hypothesis is that all these all our goals can be framed in this way. So we can abstract out the process such that each step is going to give us one numerical value that we define. We can use these algorithms to maximize the cumulative reward. A graphical representation of this could be, well, this is a graphical representation where we look at different components. So imagine that this mimics the behavior of dog. The dog is trying to learn whereas it has to fetch the stick. So the environment, who is going to be the owner of the dog, is going to throw out that stick, and the dog has to choose, the dog robot has to choose where is it to run towards the stick, fetch it, or where it run somewhere else. He's going to get some reward out of it, like maybe he'll get a treat, and that is good. If it gets spanked because it bites the owner, that's bad, so it learns to avoid it. So the dog is the agent and its movements are the actions. If the dog perceives reward as a treat in response of its action, the reinforcement learning algorithm is going to learn to take those decisions, steering it towards repeating that action later on in the process. So I mentioned that this is a Markov decision process. I think that that's a little bit too mathematically involved. So what is important here is that whenever you see the Markov property or the Markov word in math, most likely means that your current step depends only on the prior step. It doesn't depend on any step prior to the last one. So you can reduce that to a single decision step, but in the end, you look at the global picture. And just to highlight, in contrast to supervised learning, we don't provide any examples. And in contrast to unsupervised learning, we're not looking for a structure. Instead, we're trying to use the environment to maximize those long-term rewards. Does the Markov property a necessary assumption for reinforcement learning? Is this done to save computation? In a sense, yes. So that's a great question. So I think that what you say it's accurate. You need to model somehow the state, and we're going to get into this key concept. But if you want to store the whole history, it'll get your state representation. The distribution of the state representation is going to become really sparse, because it's going to, the longer the length of the observation is, less likely that you have seen it before. Therefore, the Markov decision property is a way to curtail that sparseness, such that in the end, like if you're a taxi cab robot, or like if you are one of those Tesla cabs that were just announced, it knows if it's in a current place and it's trying to reach that goal, it doesn't really matter where it got from. The important thing is the current state. So yes, it saves computation because it doesn't have to process as much data. So breaking down the concepts, state representation is the current situation of the agent. I think this is a little bit abstract, but maybe it's going to get clearer as soon as we see the notebook. The actions are the possible responses of the agent. So we're going to call an agent the robot or the program that drives that Markov decision process. A reward signal that has to be a numerical quantity, either positive or negative. So positive is good, negative is not. So in the end, an agent at the beginning is going to start exploring the reward space, the state space, and sampling the reward. Is going to learn how to discriminate against going towards directions where it sees a negative reward. And the policy is a set of rules that determines how the agent selects the actions based on the state it is in. So a policy is basically what we're trying to learn. That means, like, I am currently on state A, and I have 3 choices of action. So given my state, which of these 3 actions I have to take? In the end, like, I can observe immediately, like, if I step into either of those, I'll see a different reward. So I can use that to learn which is the next step. But since reinforcement learning is all about maximizing the long-term reward observation, maybe the immediate highest reward next step is not the best one. So we're trying to learn how to choose the action that will transition us to the next state that maximizes that long-term reward. So this is going to be a neural network, is going to be a regression model, or is going to be a table that contains just a score depending on what type of process you want to model. The return is just that accumulation of long-term rewards. So that is the actual quantity that you're modeling using a policy. So the input to the policy is going to be the state and the action. The output of the policy is going to be an estimated return. And in order to estimate this return, is going to make use of value functions, which is just a partial estimate of that return. That just basically means, like, what is the value, like, in the current state that I am, what is its current value? And you should steer towards states that have better value than others. The environment is the physical simulation of the process that we're trying to model. So what what is the difference between reinforcement learning and deep reinforcement learning? Basically, as I was mentioning here, the policy could be anything that can be learned. When you use a deep neural network to model that policy, it becomes deep reinforcement learning. So deep neural networks are just a family of algorithms that are a generalized function approximator. Simplifying it a lot because it's in reality it's actually very complex. But you can think about it as a subfield of machine learning that merges this RL with neural networks. So the advantage of using deep reinforcement learning is that it allows us to leverage all these new capabilities, hardware capabilities, like using NVIDIA GPUs, using transformer large language models, using vision language models, such that the state of something is an actual raw observation. By raw observation, I mean could be this screenshot here. So there is a very famous deep reinforcement learning paper of 2015 on the Nature magazine that kickstarted this field. And what they did was to train a deep neural network to learn how to play Atari games and be better than humans in all of those games. So the way they did it was that like conceptually really simple. This the agent was able to see only the screen. So the environment was a screen and a score. So on those old games, I don't know how old are you. Atari is actually a little bit older than I am, so I know about Atari. But think about Super Nintendo or something like that, in which you had like Space Invaders, and you got a score that incremented as you were destroying the ships with the laser, or if it was Pac-Man or something like that. The more fruits that you ate, or the more dots that you ate, you increase the score. Or if it was ping pong, like the number of bounces that you get increases the score. So we get the signal out of an emulator, but we can also see the rendered image. So as you might be familiar with, when dealing with raw inputs such as images, text, or speech, neural networks are great because they can take them in the raw form, and we don't have to do any sort of feature engineering. And they can be used to decide what is the next action. So in the Atari example, actions are what could we do as a gamer. So we had a controller that had a few buttons. So with Atari, I think it was just a joystick and one or two buttons. So you could move the joystick in one of four directions and press one of two buttons. But if it was like if it was PS5 or Xbox One X, you'd have like 500 buttons on the controller and then two sticks and then like the pads below. It's the same thing. You have a discrete set of actions. So deep reinforcement learning, what it is able to do is to take the actual image that you see on the screen over time. So it'll take the frames, it'll read the score, and it'll tell you like, now you should press this button. Of course, you're not going to press it yourself. You're going to direct the computer or simulate that press of the button, and it's going to drive the character and it's going to drive the game. In the end, because of these characteristics of neural networks, we could run it indefinitely. The like 2015 Atari was also it's really easy to emulate. You can think about it like, I'm not trying to trivialize it, but it's already a solved problem. So you can run the emulator and simulate the game relatively easily. So based on hundreds of thousands of repetitions and seeing all those frames and being able to read the score as a reward signal, seeing the actual render frame as the environment, and using the button presses as the actions, learn how to play. So we didn't provide demonstrations. Instead, the reinforcement learning algorithm was able to train a policy that choose which button to press. But this is just one example, and like it's fun, but it's just for the laws, right? So we want to do something useful. Um, there has been a lot of development on what we can do with reinforcement learning. And if you've been using ChatGPT or any other conversational language model, it actually used reinforcement learning to be trained to maximize human preferences for the responses. That is why it's so good um, to emulate the preferences of humans or of people. So I want to circle back, Nathan, to your question. There is a loss function. So the loss function is to it could be there's something called the Bell equation, Bellman equation. We're not gonna get into that today, but it's just a way to estimate what is the long-term return based on the cumulative rewards up to a certain point, and the value function as the estimation of the remaining of the return. So in the end, with that equation, you can derive what is the next update to the value and use something like least mean squares of the output of the Bellman function and the actual realized cumulative long-term return to do some backpropagation and update your parameters with any type of optimizer. Could be Adam, but any Newtonian type of optimization algorithm work. Yes, and the last function here is maximized. So the implications is that just negate it. So when you're doing deep learning, you're trying to minimize the loss. But since we're trying to maximize our reward, just take the negation of the reward to minimize it. So you're trying to get the smallest, like the most negative value that maximizes the reward. Okay, so I think that goes into the theoretical crash course of what is deep reinforcement learning. So some other examples of what has been done with it is AlphaGo Zero. So AlphaGo is a deep neural network that learns how to play Go, which I don't like. I've heard that it's like extremely complicated, but now the computers are able to beat any human being because they basically have played an infinite amount of repetitions. Um, Bird, Cell Play. Oh, this is new to me, but like it's cool that vehicles can drive themselves. So I suspect that sailing is simpler than driving in a city because there's less traffic and there like you can just move around wherever you want. Of course, maybe like a storm will complicate the process. Locomotion behavior, DeepMind's researchers. Oh yeah, so this is robots walking. So if using the Boston Dynamics robots, they like first they were trained using physical simulators, but then the actual algorithm is able to drive the robot on the real world and take those measurements as an improvement to the policy. And then here are others. So there's lots. So I just want to add also that, as I was mentioning, there's something that if you follow the generative AI news stream, you may have heard about reinforcement learning with human feedback. So this is a way to train a policy. So a policy could be the large language model. And the actions could be, what is the next token that I want to predict? So I have finite number of words. If it's, it's finite, but it's really large because it could be any possible word on any language that is spoken by people in the world. So presumably it's like it's multiple million tokens or different words, but still it's finite. It's not an infinite amount of words. So which one to choose? And traditionally large language models are semi-supervised, meaning that we scrap contents from the internet and we use those contents to teach it how to predict the next word. That means that there's no one who actually labeled that. Instead, it's data that was produced naturally or organically by writers on the internet. But when you give it instructions like, translate this text from English to Spanish, or, answer this question out of this paragraph. There are multiple ways to answer it. So you can rephrase an answer in maybe an infinite number of ways, but some of those are going to be better than the others. And we can quantify that. So we can give it a score in a Likert scale, like this is the best one, A, then second best, B, C, and so forth. So that can serve as a reward model. So best one is reward 1, second one is reward 0.75, the middle one is 0.5, and so forth until the worst one is reward 0. So with reinforcement learning with human feedback, what OpenAI did and like the industry has done is that they use the LLMs to create multiple responses to instructions and rank them. So I, as an annotator, I'm going to go in and rank, this is the best one in my opinion, the second, the third, and so forth. They're going to repeat this for like, I don't know, tens of thousands of examples with multiple annotators. And then they're going to use that to train a supervised reward model such that this can be automated. And then they're going to plug in that supervised model into a reinforcement learning algorithm that uses the LM to predict or to complete the sequence, generate the rewards based on that reward model, and train itself again, and then repeat that process. So that's a really clever way of mixing reinforcement learning with supervised learning, or an application that has a widespread use. So we all use LLMs today to automate our productivity, and it's not necessarily like teaching a robot how to move or how to get a grip of objects. So in reality, since decision processes are abstract mathematical constructs, as long as you can map something as a sequence prediction, you can frame it as a decision model, Markov decision process mathematical construct. So now let's go to the notebook. So we are going to, first I want to show you, let's see if I can make this bigger. This is a notebook that it's on GitHub. It's a little bit tricky to replicate, but if you like, because your libraries get deprecated. But the idea is this. So we have a simulator of a lunar lander. So the lunar lander is a vessel that is trying to land safely without crashing into the moon's surface within the goalposts. So this lunar lander is being pulled by gravity, and it has momentum and inertia. So it has certain propellers that allow it to be steered in a specific direction and reduce the acceleration of the gravity. So the idea is that by inspecting the state, meaning like what is the position of the ship with respect to the goalposts, what is acceleration, fire those thrusters such that it lands safely. And at the beginning, you can see how it crashes because it's not really good. We're not doing it ourselves, so it's just a computer. But how good a program that is able to use reinforcement learning to solve this look like? Well, the first step is that we need to define what is our action space. Action space. So we have multiple choices. Say that we, like each millisecond, we decide to fire one of the thrusters. So we could do nothing and just let the gravity keep pulling the lunar lander, or we can fire the left thruster, or fire the main engine, which I guess is the one that pushes upwards against the gravity, or fire the right thrusters. So we have 3 thrusters and the option of not doing anything, just let the gravity pull us. We are going to see at any time step an 8-dimensional vector. So what does a vector has to do here? Well, hold on. Okay, yes. So we need to get a hold of what is the current position of the ship. So we get its coordinates. So we're simplifying this as a 2D plane. So what is its x and y coordinates on that 2D plane? Its linear velocities. So how far is it moving on both directions? Its angular velocity, because this ship can rotate. So if one thruster is fired with a different string than the other one, it might just rotate, and we want to land upside, like on its feet, right? And we are also able to figure out whether each of the two legs is on the ground. So like maybe one lands before and then the other one lands. So if one lands and the thruster of the opposite direction fires, is going to um, drop the ship right on its side. So you can see that it has two legs. Um, and then we have to define a reward structure. So that is the quantity. It's like what happens, how does that state changes when we take one of the actions. So at each step, which let's say is each millisecond, uh, we're going to define the reward based on this specific criteria. So this is where the actual handcrafting and the feature engineering goes to. It goes into designing the reward. So for each step, the reward is increased or decreased, the closer or further that the lander is to the landing pad. So we want to move it towards that landing pad, which is between two goalposts. We want it to go slower because if it's too fast, it's going to crash and it's going to get destroyed. We don't want to get tilted. So if the lander is tilted, then we get a negative or we decrease the reward. So we want to maximize that reward. Nathan, so what you have to do is that you need to open Colab and then go into File and then open Notebook and then paste the URL. Okay. And then we're going to increase the reward by 10 points each time that a leg gets in contact. So we want to get both there. If maybe we landed and it didn't fall, and it's like on thin ice, well that's still probable, but we want to land on both its feet. And we want to minimize the amount of thrust that we apply. So each time that we fire an engine, we're going to decrease the reward. So how did we came up with this structure? It's just like a hyperparameter tuning game. So people came up with this structure such that the process is able to find a good policy to fire the engines properly. And finally, we get the final reward of the episode. The episode is when we finish. So it could be when we land in the landing pad or when the ship crashes. So if we didn't succeed, the reward is going to be negative. It's going to be decreased by 100 points. But if we landed successfully, it's going to be increased by 100 points. So we're going to consider an episode successful if we score 200 points. And we also need to have starting state. So the simulator is going to place the lunar lander somewhere on the screen. It's not going to be the same always. So we're going to see. I'm going to glance through the code, but first I want to show you how does it look after running reinforcement learning. So you can see how each time it gets closer and closer to the goalpost. And you can see how it balances better each time. Maybe there's a regression, but that's in the long run, like on the average, it's going to be improving time after time. And you can also see how the surface changes. So it's not always the same thing. It doesn't really matter because the policy learns how to distinguish between the distance of the lunar lander and the goalpost, even if we change the position of the goalpost. So you can see how the landing becomes a little bit smoother each time. So it gets to a position in which it decreases the speed significantly and it lands gently. So it's almost there. This one was almost, well, actually, I guess that was a success because like it slided. This one landed straight into the path. This was not a success. So you get the idea, right? Um, so comparing that with the actual GIF at the top, you can see how like this was a train wreck basically. Like it was just randomly find the thrusters such that it fell um into the ground incorrectly. Okay, so there is a library called Gymnasium that contains these simulators, and we have we have an agent class that contains a neural network. So this neural network is going to be a feed-forward network that contains basically it takes as input the state and then just outputs the vector with the four separate states and picks the one that's the best one. We're not gonna get into the details of this, but with code like this, you can just code a neural network to work as a score. It's actually quite long. Okay, so if you want to play with it, you can specify which environment you want. The one that we saw is called Lunar Lander V2. If you try to download this today, this one's deprecated, and then there's Lunar Lander V3. But using like there's a common interface to the environments where you get the action space, which is basically an n-dimensional vector. So you need to fetch the number of actions. You need to reset the environment such that we get the random initialization and get the size of that observation. So we will create an instance of this DQN. DQN stands for Deep Q Network. Q-learning is a generic name of an off-model reinforcement learning algorithm, and we're going to train it. So we're not going to run it right here, but we're going to look at how does it looks when we train it. So we run an episode. An episode is the chain, the whole chain of actions. That means like since we start until we crash or land. So the return is getting maximized each time. So on the 100 episode, the return was negative 259, which is pretty bad. But after repeating it, you see how the trend starts wiggling around, but with a positive trend. So this one was significantly better. Then there was a small regression, but in the end, it's trending upwards, such that after repeating landing 700 times, we finally achieve a return amount that is considered a success. And if you see that we can repeat it, and then it could be that in this specific episode, the 900th, we didn't get lucky and we got something that wasn't a pass. But in general, in average, we were able to get that return maximized. So say that we want to plot this, if you want to observe that, this is a good way to do it. In these plots, we see the reward. Well, the one that's on the top is the actual long-term return. When we start, we see like how the blue line that looks like all saggy around has a lot of variance. But if we take random mean, we can see how it starts to trend upwards, and we're until it gets a point that it actually exceeds the 130 return. So in the notes it says that whatever is above 200 is acceptable. So I think that somewhere around this point, yeah, I guess here, in average, it passes. So you can also see how the episodes become longer and longer, because the policy learns how to fire thrusters in such a way that it lands softer. And that means that there are more actions that are taken before landing or crashing. Um, so in this code, you can actually render a video. We're not going to do it today, but you can get an MP4 of your actual deep reinforcement learning model controlling the lunar lander. So that is one toy example of how to do reinforcement learning. We can also use the carpal environment. So I think this one is funnier, but what we see here is that we have a simulation of a cart that it's sliding on a cable and it's able to slide on either direction, left or right. And there's a pole that hinges on the cart. So what we're trying to do is to balance that pole. So we move the cart too quickly, that pole is going to fall to one side, or on the other way, same thing. So what we want to do is to teach the cart how to move, how to slide gently enough such that it's able to balance the pole and counteract the gravity and the angular velocity that might make the pole fall. So in here, this one's simpler. We can push the car on either direction, to the left or to the right. So this is going to be a discrete state. So at each millisecond, we're going to decide whether push more on either direction, stay, or push on the other. Well, actually, just push on either direction. It cannot stay put. And the observation space is similar to what we saw on the lunar lander. We have a cart position on the x-axis. This time is just single dimensional. We have velocity. So the more that we push, we're accelerating the cart each time. So if we push it multiple times, it goes faster on either direction. So it could be infinitely fast, so it can run away. We see the angle of the pole, and the angle is, as it says, like how tilted is it to either direction. And there's also an angular velocity, so it could fall pretty quickly, or it can be tilting but not moving too much. So based on this, using a DQN, we can pass a four-dimensional vector that contains these quantities and decide whether do 0 or do 1, which is pushing to the left or pushing to the right. And the reward function, again, which is the main design point of a process, is designed to keep the pole up for as long as possible. Eventually, it's going to fall, but for each millisecond or each action that we take, if the pole doesn't fall, we're going to get a reward of 1. Once it falls, the process finishes, and we end the accumulation. So one key difference here is that there's no negative reward. So we start from 0 and we just start accumulating once. That is because by design, we want to be able to run this for as long as possible. So if we are able to run it for 500 times, if each time step is 1 second, that would be 500 seconds. So could be the higher the better, right? And the cart is always going to start within this range. I'm not exactly sure of where it could be, but it's around the center. So how do we define where the pole has fallen? If the angle is more or less than 12 degrees, so 12 degrees in either direction, then it has fallen. If the cart pole position runs away, then it falls. It fails as well. And we're going to end the episode if the reward is greater than 500. So let's look at how it looks after training. So you can see how it in the first episodes it just pushes to one side and it goes away, and because in the end it's balancing the pole, but we don't want it to run away. We want it to be within the bounds, so we need to counteract the movement on either direction. So each time that it passes, you see that yes, it does run away, but it's able to stay on screen for longer, which is maximizing the reward. And how would this look? Well, we will need to use the same gene library, instantiate the carpole environment. We get the render of the screen, and well, we're getting a screenshot here. We're gonna measure, like, do some debugging. What if we just randomly execute the actions? So the reward that we are seeking in the end for each episode is about 200. If we just randomly assign an action, we can see that we're like way off. It fails too frequently. And the score. So we're trying to increase the score, which is the return signal. It is like heavily leaning towards 0 because it fails pretty much right away. Using a deep neural network such as this, in which we have multiple linear layers with leaky ReLU, which is an activation function. We can use the Q-learning algorithm, which is implemented here. So somewhere here, there's going to be the Bellman equation that I was mentioning to predict the Q values, which are the value functions. And let me see if I can find it. Yes, this is the Bellman equation. So if you're curious about it, you should read about reinforcement learning theory. But the idea is that we get the actual cumulative reward so far, and we use the predicted Q values, which represent the expected reward on the long term for each of the possible states. And we apply a gamma coefficient, which is going to dampen that reward. So the further away it is, it has less impact with the actual current state. And that is going to be the update. So with that update, then we can do the backpropagation and choose whatever state maximizes that Q function. So in that way, we can do, we're not on a greedy process. We can maximize over the long term. So if this was run and then we look at the same measures, we can see how the actual score per run at the beginning is still like pretty small, but over time it starts to go above significantly, and it's always going to be wiggly because there's randomness implied in the process, but eventually it exceeds the threshold. And you can see how the scores, if we plot a histogram, are actually not as skewed towards this left point of the plot. So what is this? There are, yeah, so there's a variation, like there's an infinite amount of flavors of deep reinforcement learning algorithms that deal with the variance of the process. But this one, DQing with replay, gives better results, such that it after a while it consistently performs better in terms of the score. That means above the actual reward goal. We can see how the actual mean of the scores passes the actual goal that we want here. And there's a new, yes, another variation of DQN with replay. The same thing. There's double Q learning. So I'm gonna glass through this because these are just variations of the neural network. But in the end, it is like you get similar results. This one might not be as good for the carpole process, but it's still performs much better than the random one or the vanilla DQN. And that's it. So feel free to run this notebook or try to run this notebook if you want. So what are the highlights of this? Reinforcement learning is a family of algorithms that allow you to learn through interacting with the environment. How does this look like? It means that you don't have to have label data. Instead, you're going to run a simulator or define a function that gives you a reward signal that works as a heuristic to tell you whether you're going in the right direction or not. With repetition of this, the reinforcement learning algorithm is going to train a policy. A policy could be a neural network, could be any type of machine learning model that predicts which action to take next. Actions are discrete. There's a continuous equivalent of this, which are, I think they're called the Kalman processes. I'm not very familiar with that, but the principle is the same. And reinforcement learning is used a lot to simulate physical processes and to incorporate hard to replicate or hard to imitate processes such as performance learning with human feedback. So it is like, if you get into the theory, it's quite math heavy, but it's actually pretty interesting. And I could say that if you're interested in the research point of view, there's a lot going on, and I think that is going to be one of the hottest, or is actually one of the hottest areas. Like if you saw the DeepSeek release a few weeks ago, they were able to leverage reinforcement learning to train an LLM using significantly less resources than what industry titans such as OpenAI or Meta are doing today. And that is basically through their understanding of the mathematical processes that are underpinning reinforcement learning. Okay, so we're exactly at 1 hour. So we have a couple minutes. Yeah, of course, Nathan, if you have any questions, please feel free to ask. Once we're done, I'm going to stop the recording.
All right. Thank you, Enrique.
All right. Thank you, everybody.
Please stop the recording.